In the third example, we have a force that's equal to negative 100 newtons per meter times x. Now this is the form of an elastic force by an ideal spring, as one example. Or it could be the force of a pendulum in small oscillations. It's a fairly massive pendulum. Yeah, not hugely massive. We're going to assume that the initial value of x is 20 centimeters and the final value of x is negative 10 centimeters, and we want to find out how much work this force does. Now this could correspond, if say the x direction is this way, we have a point where x equals 0. At that point, this force is 0, so that's kind of our reference point. So we're 20 centimeters this way from our reference point. So x is going to be in this direction. Okay, so x is going to be positive in this direction. And the force is going to be what? It's going to be in the negative direction because of this negative sign. Okay, so this object is going to be then experiencing a force in this direction. And if it moves in this direction, then its motion is going to be in the direction of the force, so that when you multiply its displacement by the force, it's going to be positive. So you're going to have positive work done on the object as it moves in this direction, at least until it gets to the point where x equals 0. Now it's going all the way to where x is negative 10 centimeters, so as it moves past this toward that negative 10 centimeter position, x is going to become negative, the force is going to become positive, but you're moving in the negative direction, so the work done by this force is going to be negative. Multiply force in the negative direction by displacement in the negative direction by force in the positive direction, you're going to get negative work. Okay, well, how much work is done, the delta W, between this point and this point? Okay, well, the work done by a force is the average value of the force times the displacement. Okay, the displacement from 20 centimeters to negative 10 centimeters is negative 30 centimeters. But now what's the average value of the force? Okay, this is not a constant force. You can't just evaluate that force at one point and say that's it. Although actually if you did that at the midpoint here, you would have the average force, midpoint of these, between these 2 points. That's not always the case. That's only the case if your force happens to be linear. Because if you average a linear quantity between two positions, where the force is a linear function of position, then the average value does occur at the midpoint. Just think of a force versus position graph. It's a straight line. The average force does occur at the midpoint if the force versus position is a straight line, if the force is linear. So I say the force is linear in x, so we could just calculate the average force. Another way to calculate it is just figure it out at the 20 meter position, figure it out at the negative 10 meter position, and average them. You can do that with a linear function. We don't want to do that because most functions aren't linear. Linear functions are cause for joy because we can shortcut what we have to do. We want to see what we would have to do in any other case. Well, what's another idea about average force? Well, average force is just the product, the average value of a function over some interval is just equal to its integral over that interval divided by the length of the interval. A concept that you should have developed fully, or as fully as possible, in first year calculus, but probably didn't because most people don't. Because there's a lot of things you got to learn in first year calculus. You learn that idea, you go on, you know the idea long enough to pass the test, and you forget it. You want to get out of that mode. You really got to retain things. However, having learned it, you can relearn it, and you really need to do that if you haven't already done so. I kind of advise that numerous times. Okay, so now the average force is the integral divided by the interval. The interval is negative 30 centimeters, So if you multiply the average force by the interval, you get the integral. So we do the integral. Now there are other ways to see why we do the integral, and even better ways to see why we do the integral. But this can be a helpful idea. So in any case, we integrate the force from here to here, and the integral is really simple, and we end up, I believe, with 3/2 of a joule. Okay, now, that's positive work. Which means what? If we start here, first place, do we even get here at the 20 centimeter position? Will we even reach the 10 centimeter position, assuming this is in fact the net force, which would be the case for, say, an ideal spring or an ideal pendulum. Okay, would we even get from here to here? Well, since we have more kinetic energy here than we had to start with, it's certainly possible to do that. Okay, we can't have negative kinetic energy, but if we start from rest, we've got 0 kinetic energy. And if we add 3/2 of a joule to that, we've got 3/2 of a joule of kinetic energy when we get here. Meaning, if we start here, we're going to get here, and we're going to have some velocity. If you know the mass of whatever is being moved, you can set that equal to 3/2 of a joule and figure out how fast it's moving at this position. So on one level, this problem is a reinforcement of what it means to have an average force, and a comment on what you can do since this is linear to shortcut the integration. But then it's an illustration that you just integrate force with respect to x, and you get the change in kinetic energy, assuming that this is the net force, which is a condition of the problem. Okay. So, in matter of fact, I should probably put a net on this force and a net on this force to indicate that we're talking about a net force, so that this is actually a change in kinetic energy. This is work done by the force, whether it's a net force or not. It's the change in kinetic energy if this is, in fact, the net force. Now, if there are other forces, friction might sap out some of your energy, because as you move from here to here, friction acts in this direction. So friction does negative work, and if friction does more than 3/2 of a joule of negative work, you ain't going to get from here to here. You're going to stop somewhere between here and here. You want to think about that. Okay. But again, on the most basic level, you got to integrate your force with respect to position to find the work done by that force.